welcome everyone for the next session of Introduction to Biomedical Optics from Theory to Applications in this SOAM portal. Today we will talk about a very important topic which is known as coherence. Coherence is an important topic because of the many applications tied up with the coherence. Coherence is basically a property of a laser, because that is the only system that actually obeys coherence in a greater extent. Otherwise, the other light source that we see in our regular life, that is like LEDs, fluorescent light, sunlight, all of them actually don't have a higher quantification in the coherence. So let us try to understand what is coherence. Coherence can be divided into two sections. So there could be two types of coherence. The first is a spatial coherence, another is temporal coherence, right? So as we know that we live in, as Einstein told, so we are not just staying in the 4 dimensions, that is the space x, y and z, but also the 4th dimension, that is time, right? So the world can be quantified not only with space but also with the time, right? So similar to that, in coherence we have both spatial coherence and the temporal coherence. So let us try to understand what is the difference between spatial coherence and temporal coherence. You can see these few of the figures on the right hand side of the slide, and it shows like what is a kind of a meaning of a coherence. So you can see that army, a band of people from the army, they are actually marching along a particular line. So you can actually say in roughly that it's kind of coherent, right? So we are not as of now telling like whether it is temporal coherence or spatial coherent. You can just mark it as a coherent as of now, right? You can say that some part of it in the bottom image, it's partially incoherent. So you can see that some of them are actually walking together, and the other of them are, so they are actually walking in groups, right? So few of them were walking together, and then someone in the back side they are walking together, and then again in the back side they are walking together. So it's like kind of something known as partially coherent. So it's not all of them are walking together in a particular line. So we can actually say that it is a partially coherent. Now the one on the right hand side, which is kind of a street where everyone is just walking randomly and there is no kind of a correlation that is actually happening, right? So this you can actually term it as incoherent, right? So similar to this, we can quantify the light source as well as coherent, partially coherent or incoherent, right? Now let us start to understand what do we mean by temporal and spatial coherence. So on the left hand side, what you see is on the left hand side is the definition of the temporal coherence. On the right hand side is the definition of spatial coherence. So let us now focus on only the temporal coherence. Now the temporal coherence is defined as the from the phase of the light, right? Now this phase actually varies. So you take any of these light source in your nature, the phase of the light actually varies, right? So it goes up and then down, then again up and then down. Now if the change is kind of uniform, right? So if you see a very uniform change of this phase, then it is kind of known as a temporal coherence, right? Now but we don't get such kind of a perfect light source which is having a very uniform variation of this sinusoidal wave, right? There would be always some fluctuations, right? So it will not be a perfect sine wave, but there would be also some kind of there could be some kind of fluctuations in that perfect sine wave, right? So on the right hand side you can see that there could be some that is the same sine wave with some kind of fluctuations, right? So so now it's not a temporal coherent light source. On the left hand side, which is kind of perfect light source, where the sine wave is like perfect, right? So at that time it can be told as a perfect temporal coherent light source. On the right hand side, it is having some kind of an offset along that particular phase, and that's why it is not a perfect temporal coherent light source, okay? The perfect light source, the perfect temporal light source can also be told as a if you consider the change in that phase along that the phase change to be like as minimum, then it kind of told as monochromatic light source, right. Spatial coherence is based upon the okay, so temporal coherence is by checking the phase along the time distance, right. In this spatial coherence, we need to see the transverse direction, that is the perpendicular to the direction of propagation. For example, my direction of propagation is this way, right. Now I need to see the wavefronts which are perpendicular to the propagation of my direction, right. So this is my wavefront which is vertical, and I try to see does the wavefront is actually vertical, or if there is some kind of a obstructions in the wavefront, or some kind of deviation is there from its original pathway, right. And if there is an obstruction, how much is the obstruction changing with respect to the time, right. So we try to understand the transverse direction of the plane wave of the direction of the waves, and how much it is actually changing at different points of that transverse plane as compared to the direction of propagation. So here you can see that this is a perfect, again we talk about perfect and not perfect light source. So this is a perfect spatially light source, spatially coherent light source. You can see that there is a uniform distance between two curves. Okay, this each curve means a wavefront of the plane wave. A wavefront could also be can be also be told as a peak of the of the wave. As you see that the waves are nothing but like having peaks and troughs, So it has a maxima and then minima, again maxima and then minima, right. Now if I take all the peaks together, okay, one by one, so you can actually trace a line along that particular peaks, then you can get this kind of lines, okay. So these lines, if they are equally spaced out as you propagate along this direction of propagation, you can say that it is a spatially coherent light source, okay. But on the right hand side, you can see that this spacing is not equal or not uniform as you go forward in the direction of propagation, right. So you can see that there are more spacing as well as less spacing in some of the wavefronts. So in that case, it is a non-spatial. The light source is not spatially coherent. Okay, so you can say that. So these are the two definitions of the two different kinds of light source. How you can define the different kinds of light source: temporal coherence and spatial coherence. Now let us dive deep and try to understand how do we quantify this temporal coherence, how do we quantify the spatial coherence, right. So now there are few of the parameters that we can use to define this coherence. The first one is known as temporal coherence time, right, and another is defined as spatial coherence length, right. So this time and length is what we are going to quantify for many light sources. So in our case, we will quantify these coherence parameters for 4 different light sources, that is helium neon laser, we will do it for LED, we will also do it for diode laser, and finally we will do it for halogen lamp, right. So let us see how do we actually define these parameters. Okay, so now let us try to understand visually what do we mean by temporal coherence and spatial coherence. Now you see the graph on the right hand side top. What you see, as I was always saying before, that a wave actually has max and minima, right. Now the same max I am just drawing over here, minima I am drawing over here, then again max, minima, right. So max min you can see over here, and it's a kind of a straight line because the peak also has a particular line. So this wave is going up and down, but out of the plane also it's like extending to infinity in one of the hypotheses. So you can see that there is a max, and so the spacing between the max and min is the same. There is no change in the spacing as you go forward in the direction of propagation, right. So the spacing is uniform. Also the bend, there is no bend in the peaks of the wave, right? So there is no bend. So you can say that this is spatial and temporal coherent. Yeah, it obeys both spatial as well as temporal coherence. Now let us see this one. So what I would recommend is that you can pause this video and try to think about what we discussed in the last a few minutes, and based on that, can you tell me whether this is spatially coherent or temporal coherent? Okay, so I think that you would have already paused this video and thought about it. So this one over here, what do we see? So we see that the wavefront is bending. Okay, however, the spacing between them is the same. Spacing between the two wavefront is the same. It's equally same throughout the propagation, but the wavefront is bending. You can see, right? So when we talk about the wavefront, that is nothing but the transverse direction of propagation of our light source, that is bending. So so that is related with the spatial part, right? So in that case, we can say that it is spatially incoherent, right? But it is still temporal coherent. Why it is still temporal coherent? That means the distance between the max and min and max, again max and min and max at each intervals is the same, right? So if that is the same, the distance between the max and mean as with respect to the time for multiple of the maxes and means are the same, that means that it is temporal incoherent. Sorry, temporal coherent. Okay. Now let us see this one. Okay. So here again, can you pause the video and try to understand whether it is temporal coherent or spatially coherent? Okay, so what do you see over here? You see that this is again a max and the mean comes very close to the max. Okay, and then the max actually is very far away from the mean. So it's like very high peak, and then there is the mean peak is, the minima peak is coming very quickly with the max, and then the max peak is very far away, and then again mean peak is very far away, and then max and mean are very close by, and then the max is kind of very far away, right? Now what do we see from here? We see that the transverse direction, this is the wavefront, is kind of they are like on the same path, right? Or they are kind of aligned, you can say, right? They are collinear, they are aligned, all the phases are together over here. So this, you can say that this is a spatial coherent light source, right? But what about the temporal? Yes, you can see that as with respect to the time, the phase, the distance between max and mean and max and mean are varying. They are the time distance is not actually uniform. So you can say that it is a temporal incoherent light source, and it is spatial coherent. Why it is spatial coherent? Because in the wavefront, all the peaks are coming at the same time, transverse to the direction of propagation, right? Now, what about this one? Now I just take both of them together, and then it's kind of, this is kind of very easy to understand, of course, because this is the superposition of this and this the attributes, right? So now we can also say that it is both spatial incoherent and temporal incoherent light source, right? So this is how you can actually visually understand the difference between the spatial as well as temporal coherent of the light source, right? Now again, so how do you define these coherence parameters? As we discussed some time back, we defined using coherence length, which is given by L underscore L subscript C or LCOH, that is coherence length, right? So that is nothing but defined as the propagation distance over which the beam is actually coherent, right? So if you shine a laser light source, it would be coherent for a particular distance as well as for a particular time. If you have a stopwatch, you can actually see how much time it is actually coherent. Of course, this would be in a very small period of time because the light propagates very quickly. So the coherence time is kind of very difficult to calculate. experimentally, but you can calculate this length of the light source which is coherent, right. So coherence time, that is the time that it is going to stay coherent, right. By coherence means we are talking about temporal coherence as of now, right. So the temporal coherence is defined as a ratio of inverse of delta of nu, right, and delta nu is nothing but the spectral bandwidth, right. So if you tell about any of this light source, right. So if you tell about any of the light source, for example a light emitting diode, the spectral bandwidth, for example I am using a red LED light source, so it would be having a spectral curve like this one, okay, having a peak of around 630 nanometers, okay, spectral wavelength, spectral um, intensity. So this is nothing but wavelength, and the y axis is nothing but the intensity, okay. So when I am talking about the LED, that is, you can see that the full width half maximum, this is known as full width half maximum, is kind of very high. Now when we talk about, so this is for the LED. Now when we talk about the laser has a very small FWHM, right. So this FWHM is nothing but your delta nu, okay, this is nothing but the delta nu for LED, and this is the delta nu for laser, okay, this is for laser and this is for LED. So you can see that for the LED, the delta nu is kind of very large, right, and the delta nu for the laser is kind of very small. You can see from this curve, okay. Now as our temporal coherent time is inversely proportional to the spectral width or the full width half maximum, the temporal coherent time for the laser is of course going to be more as compared to the LED, right. That is what we will see as well in some time. Now coherence length, that is defined by LC, is given as the speed of light into the coherence time, right. So both of the parameters we can actually quantify. For each light source we can actually quantify the coherence time as well as coherent length for each of these light source. Now for example, you can see, now we can visually understand now what is coherence time and coherence length, both of them. Now you can see that this is for helium neon laser that you see in this image. It has a very long coherent length, right. So it's very long, you can see that, and the volume of coherence is also significant, right. So it's a volume of light source, because it's not kind of a point light source, it has a particular beam, and that beam is actually propagating. So the beam is having pi r square into the length of the propagation, right. So now you can see that it has a very long coherent length, and eventually it will also have a very high coherence time as well. Now let us see for the light emitting diode, right. So light emitting diode is having a significant bend in the divergence, so that is why it is actually bending in the adjacent regions, and it has low coherence length, right. You can see over here, because this is the coherence length, which is significantly smaller as compared to the helium neon laser, and that one of the reason is the spectral band, which is kind of significantly lower as compared to the helium neon. You can see for the diode laser has a, a spectral width between the helium neon laser and the light emitting diode. So you can see that the coherence length also is between the helium neon laser as well as light emitting diode, okay. You can also see for the lamp, which is right now on the right hand side bottom, you can see that it has the lowest coherence length as well as the lowest temporal coherence as well, temporal coherence time as well, right. that is again because the spectral width of the lamp is kind of huge. So, but we can actually convert it into a spatially as well as temporal coherence, as we see in the end of this class. We can still convert this lamp into a coherent light source by applying some kind of filters and pinhole as well. So now let us see in the values, right. So here you can just see, I am just trying to conclude for or summarize for the 4 light source that we use. For laser, it has a very high temporal coherence, but at the same time and it has a very high spatial coherence as well. For light emitting diode, it has low temporal coherence, but it has a high spatial coherence. So you can see over here. So the spatial coherence is more in the light emitting diode. So what do we mean is that the wavefront are actually are on the same transverse direction as the light actually propagates. So it is able to sustain its wavefront as it propagates along the pathway. So it has high spatial coherence but low temporal coherence. Okay. When we talk about the lamp with spectral filter, so this is what we will talk about at a later point. So spectral filter is nothing but a kind of a filter which allows only a certain band of light to pass through. So a lamp, which is this lamp, which is having a white light source. It's a broadband light source. You give a white light source and then I apply a filter in front of this lamp. For example, a green light filter. So now only a green light will actually pass through. So if I do that, it will have a low temporal coherence, but it will also have very low spatial coherence. So both would be poor in this case. Right. Now when I apply a lamp which is like without the spectral filter, it has both very low temporal coherence as well as very low spatial coherence. So it will be something like this one. Okay. So based on the applications, we actually need to change it. Now let us see one of the example of the light emitting diode. As I told you some time back, each of this light source has a spectral bandwidth, right. So you can see this is a spectrum that is given in any of the data sheet that you buy this light emitting diode or the lasers. And we also discussed in one of the data sheets in one of the sessions that we were discussing the data sheet, how to read the data sheet. So in that also we discussed about such kind of spectrums of the light source. So this is the spectrum of the light source. The central is is around 1 micrometers. So this is the central, that is the peak wavelength is around 1 micrometer. So this is kind of an NIR LED. Okay, and the bandwidth is around 50 nanometers, right. If it is 50 nanometers, means the delta lambda, this one delta lambda would be around 1.025 micrometers. Okay. Now we have been asked to calculate what is the temporal coherence time and coherence length. So how do we calculate it? So now we convert this into a frequency spectrum, right. So now it's important to convert your wavelength domain to frequency domain, right. So now if you convert this with a simple formula, C equal to f lambda, right. Now we can also f is nothing but the nu over here, right. So we need to convert into this. So 1 micrometer corresponds to 300 terahertz, right. If you use this in this equation, you put this 1 micrometer over here and then you put the 1 micrometer in the denominator over here, then you calculate nu. So nu is nothing but 3 times 10 power minus 8 divided by 1 into 10 power minus 6, right. So you can see that it will be around 300 terahertz. Now what is the corresponding value of nu of lambda 1 equal to 1.025? If you do that, you will see that it's around 292.68 terahertz, right. And similarly there is one more value over here on the left hand side. So what is the delta nu? Delta nu is nothing but 2 times into V1 minus V0. Okay, so that is nothing but your spectral, not the spectral, not the spectral width, but now it is a frequency bandwidth. Okay, so now what you see over here, you calculate this both the things out, and you will find that your delta nu is nothing but around 1.5 times 10 power 13 hertz. Okay, this you can actually calculate. You can take in the denominator and you can find the coherence time. So what is the coherence time? Coherence time is around 67 femtoseconds. It's like very less. If you want to do such kind of applications, we want to use an application where coherence is required and you want to use LED, then you have to work within that 67 femtoseconds, which is kind of very, very less. Now you want to calculate the coherence length, right? So coherence length is nothing but around just multiply your speed of light into this coherence time, which comes around 20 microamperes. Again, very, very small, very, very. So it will only work for a very, very thin domains. Okay. So now let us see the different values of your delta nu coherence time as well as your spatial coherence length for different light source. So if you see for the filtered sunlight, it's around 3 times 10 power 14. It's again in order of femtoseconds, and coherence length is as less as 800 nanometers. Like what will happen in this 800 nanometers is our hair itself is around 60 micrometers. So you can assume like how thin do we need to work with to get this kind of coherent properties still be sustained after the light actually propagates through such kind of media. Light emitting diode, it has a coherence time of around in order again hundreds of femtoseconds, which be kind of very difficult to work, and then around 20 micrometers, again very thin for this to work with. Low pressure sodium lamp, again very less, around 2 picoseconds, and then 600 micrometers. This is kind of okay, because when you talk about working with microscopic slides with very flat, very thin tissue samples, then yeah, this could actually work, because that slices, the slices would be, the tissue slices would be in order of hundreds of micrometers. So those would be also a thing that you can actually work with that. And when we work with helium neon laser light source, you can see that now it raises to around 20 nanometers, 20 centimeters coherence length, and your temporal coherence time also, is now in order of nanoseconds now. So now it actually you can actually quantify, you can use the parameters with which there are tools with which you can actually work with nanoseconds order. Single mode helium neon laser, it has around 1 microseconds of temporal time, coherence time, and then coherence length is around 300 meters, so like significant, very significant light source. Yeah. So so this is what we actually quantified some time back, right? So similarly, that like similar to this, you can actually quantify for others as well, right? Yeah. So now when you see the helium neon laser, during this period where you see the coherence length, where you observe the coherence, you can assume it that the phase of the light source, they are marching together in the same phase. Not much loss in coherence, but outside this regime, you will see that it's actually partially coherent or incoherent light source. In the case of light emitting diode, you can see that a very small period of time, the phases would be marching together, light source would be coherent, and for the other period of time, it would be either partially coherent or it would be incoherent light source. Okay, so let us see another example. When we talk about wavelength, or we talk about now a laser which is having a operating wavelength of 600 nanometers. Okay, and this could be a laser diode, very poor laser diode, maybe a semiconductor laser diode, and having a bandwidth of around 2 nanometers. The corresponding delta nu will be calculated as 1.66 times 10 power 12 hertz. You can use the same formula that we used earlier to calculate this. You put this in denominator and you get around 6 times 10 power minus 3 seconds, and this is the temporal coherence time, and this is the coherence length. Again, it's order of around 180 micrometers. So something like you can still use on microscopic slides if you want to take this coherence properties. Right. So let us see few of the applications, so which actually motivates us to use this light source. So why are we working so hard to get this coherence into our systems? So one of the application is on speckle contrast imaging. Now when we shine the laser on our hands, or on our desk, for example, you can see that there are some kind of bright spots and dark spots. right? So those are known as the speckles. Now what happens when we shine the light on your disk, that speckles, that bright and dark spots, they don't actually move, they are stationary. But now if we talk about on if we shine the light source on the blood vessel, right? So in the blood vessel that you see, or any of our arteries or vessels, or the veins, you will see that the speckles will actually move, as you can see over in this diagram, right? So they will actually move with respect to time. Now that movement of the speckles are actually correlated with the speed of the blood which is flowing in that artery or the vein, right? So it's nothing but with the interference and of the light source, and for that we need a very high coherent light source, right? So you can actually quantify the blood perfusion rate for with such kind of applications. One more example is a detection of gravitational waves. So this was actually also was eventually performed recently in the using the Michelson interferometer in the LIGO interferometer, and they were able to detect the gravitational waves. So for this such kind of application as well, we need a very significant coherent light source to detect such kind of very weak signals. Okay, so now let us see, as we now move from now we have understood what is a coherent light source, spatial coherent light source as well as temporal coherent light source. Now let us see for biological applications what kind of light source we need to use. More or less we use a light emitting diode and the laser diode. So I have written what is the coherence length for both of them. So based on that, let us try to see what for different tissue types what would be the cases. Now the first case that we see is a monolayer of cells. So we we take the microscopic slide, and on that we actually put few cells of put few cells so that they are on the monolayer. Monolayer means one by one on the stacked on the same platform. They are not over, so there is no one cell on top of another. In that case, that dimension, that is delta L, that is the thickness of your cells, would be in order of tens of micrometers, right? So in that case, if you shine the light source, you can expect the light to stay coherent once we are detecting, right? So in that case, we can use either a light emitting diode or laser. Now let us take a cuvette. Now this is a cuvette, and in which in this cuvette we put many cells together in that cuvette along with the analyte, right? So now the cuvette dimension is in order of centimeter or in tens of mm, but because the cells are like are kind of surviving by or they are kind of moving here and there, the domain itself is optically thin, right? So it's not actually physically thin, but it's optically very thin, because your light interacts with only a few, one or maximum two cells as it propagates through this cuvette, right? In such cases, you can still use your delta L, that is your the optically thin dimension or the optical distance that it actually propagates through, the light propagates through, is kind of very less as compared to the coherence length, and in that case you can use your light emitting diode or the laser to sustain your coherent light source. But now let us think about a bulk tissue such as the fingers that we are talking about. Again, maybe not as fingers, but again something like thick as in order of few tens of mm, like 5 mm or 7 mm or around 10 mm. Thick as our tissue is very difficult to propagate without losing our coherence, but we talk about tissue thickness in order of few mm's, perhaps not more than 10 mm. Okay, in such cases as well, you can see that on the surface of the tissue, right? Now there are two things that we can now focus on: the surface of the tissue, and then we talk about the bulk tissue as well. Now the surface of the tissue we can quantify for your so if you want to quantify the surface properties, right? If you want to quantify surface properties, in that case you can still use LED, because it would be having a small thickness where it could be surviving its own coherence. But if you want to calculate the coherence, you want to calculate the properties of the bulk tissue, in that cases you need to use only the laser light source, because it is significantly longer and it's turbid media perhaps, so there will be a lot of flow as well. So in such cases, flow of many tissue constituents, could be blood for example, and in such cases we could only use the laser light source. Okay. So now let us see how can we actually create a coherent light source. Again, it will be not as high coherent as what helium neon is creating, but it still we can actually create a coherent light source using a incoherent light source like lamp in our case. So now we have an incoherent light source, which incoherent light source means it is purely incoherent, means it is a broadband light source. It is not a monochromatic light source, a broadband light source, that is a temporal incoherent, and spatially incoherent means the wavefront is kind of very very ambiguous. Okay, it's not kind of straight, but it's kind of in many angles drawn together. So you can see that we can use a pinhole aperture. Okay, we can use a pinhole aperture to make the wavefront coherent, right? So now we have a spatial coherent light source. Once the incoherent light source passes through a pinhole aperture. Now we want to make a temporal coherent light source as well. So what do we do is that we use a wavelength filter after this light, after making the light source spatial coherent. So once you use the wavelength filter, for example, I am allowing only a small band of green light to pass through, right? So after which I can get a temporal coherent light source as well. So now what we see over here is a spatial and temporal coherent light source. Okay. Now one of the example that you see is a double slit Young's double slit experiment. It actually demonstrates the spatial coherence, right? You can see that your the water waves are propagating and then hitting both the slits together, and then it becomes a coherent, spatially coherent light source, right? So this is one of the example. Just for demonstration, I just showed to you how do you see the spatial coherence in real life as well. Okay, so that's it from our side on the. Thank you.